I'm Neil. This chapter is all about the propagation of mechanical waves and sound. Now, if we take a look at the picture here, if you've ever been to a cave, this is in Guilin in China, southern part of China. I took this picture inside of this cave. Maybe you've heard the sound of your voice coming back at you if you speak loudly enough. That is your echo. The sound, as it leaves your mouth, it bounces off the cavernous walls and the stalagmites and stalactites, and it gets reflected back to you. And there's a time delay for this to happen, typically a few seconds or so. Now, in this chapter, we're going to learn all about these mechanical waves, the propagation of sound, and the sound as it propagates is actually a pretty interesting thing. It depends on all kinds of things, the chemical composition of what it's reflecting of, the temperature of the atmosphere, for example. And so we're going to find out how all of this is put together. Let's pull up the chapter here. And waves, it's a propagation of energy. All waves are a propagation of energy. Some waves can go through different kinds of materials much more efficiently than others. So we're going to talk about examples of those as well. Now, there are different class of waves called electromagnetic waves, which we'll get to in a whole separate chapter. Those waves propagate through vacuum, as well as material matter like solids, liquids, and gases, but we're not going to talk about those just yet. We're going to talk about mechanical waves that actually needs a medium for their propagation. Now, waves in general, like I said, requires a medium. So it's the transfer of energy from one point to another, and the medium is what transfers the energy one particle at a time, one atom at a time, one molecule at a time. So, for example, the sound of my voice, the vibrations are being transmitted as energy from one molecule to the next, to the next, to the next, until it gets to the microphone, or maybe a listener, a person that's listening to my voice. If you can actually see what was happening, you would see that the molecules of the material that's transmitting the sound is transmitted one of two ways. Either the vibration of the media is back and forth, left and right, and these are called longitudinal waves, where the direction of oscillation is parallel to the direction in which the energy is flowing. That is the direction which the wave is traveling. If we were to look at a different scenario, these are called transverse waves. Now, transverse waves, just the opposite occurs. The motion of the material that's transmitting the energy, if you could actually see what was happening, each particle fluctuates up and down. Not sideways like they did for longitudinal waves. These are called transverse waves, by the way, as they move up and down. That is, their displacement is perpendicular to the direction in which the energy is flowing. There is a unique situation where we can combine both of these together and we get something called seismic waves, as in earthquakes. I'll show you an example of that shortly. But if you could look at the location of each particle, whether it be a longitudinal wave or a transverse wave, if you look at the motion of each particle, it fluctuates from its resting point. It goes out to a maximum distance, comes back to its resting point, goes back to a negative maxima, and back again. That is, it fluctuates over time and space, and we can represent such a fluctuation with a sine curve. And we can give it the properties of any wave. All waves show this particular material, displacement over time. And so we can represent all of these with these sine waves. So if we scroll down a bit more, we determine the properties, the amplitude as a function of its maximum displacement versus such things as wave number, angular velocity, and time. That's what this equation here is depicting. Here's the maximum amplitude that any wave can have. This is the location, and this is the angular displacement. All of this together is called a phase of the wave. And so we determine from this such things as the power. This represents the power of the wave. So if we looked at something like an earthquake, and we'll do just that. For example, right here. On my trip to Haiti, I did a tour of some of the regions. This is the National Cathedral, or what used to be the National Cathedral, that was hit by that monstrosity of an earthquake a few years ago. And it demolished and killed, many people, much loss of life and collateral damage. Earthquakes are a combination of both kinds of motions, longitudinal as well as transverse, up and down. And it's quite devastating because transverse waves, they travel efficiently through solid material. And remember, transverse waves, they move up and down, and we have yet to figure out how to build buildings that can move up and down. So therein lies the problem. We can build buildings and structures that move sideways back and forth like this, but sadly, that's not how earthquake waves travel efficiently through materials. They go up and down. So until we learn how to build buildings that can move up and down to absorb or dampen the effect of transverse waves, collateral damage, unfortunately, will continue like this. Here's an interesting picture here. That's me standing on a very interesting place on our planet. This is where two plate boundaries meet. In the idea of plate tectonics, the Earth has about 24 huge slabs that are floating on liquid rock, the asthenosphere. And as these plates move along, they jostle for position. Either they crash into each other at a convergent boundary, or they pull apart at a divergent boundary, or they slide past each other at a transvergent boundary. All three of these types of interactions, and there are only three types that are possible, can generate earthquakes, and these are the earthquakes that we were just talking about here. Most of these plate boundaries, by the way, and the 7 of these largest plates, we call these, the tips of them rather, we call them the continents, like the North American continent, the South American continent, the European continent, African continent, and so forth. But the vast bulk of each plate is beneath the ocean surface. We live on the very top part of the plates, much like a piece of ice floating in water. Only 10% is above the waterline. Well, the continents are just that. They are the top parts of the plates. The plates are beneath the waterline. And they're mostly these boundaries between the plates, they meet up on the ocean floor. There are just a couple of places on Earth where these plates meet up on dry land, and here's one of them. This is in California. This is called Carrizo Plains. And on my left over there in the picture, out to sea is the Pacific plate. On my right is the North American plate. And both of these plates move up like this, and they are sliding past each other at what's called a transform plate boundary. And that grounding effect, it takes a lot of energy to be built up over time to overcome the friction between these massive plates. And eventually, friction is going to be overcome, and all of the energy that went into building up to move those plates gets released over a matter of seconds. And we feel that energy as an earthquake. So that plate boundary actually runs about 800 miles along the west coast of the United States, including California and Oregon. And they come in different sections of about 100 miles or so, and they altogether they add up to about 800 miles. An infamous part of this plate boundary, by the way, is the San Andreas Fault. That's just under San Francisco. This is why San Francisco suffers from major earthquakes, 7.0 or higher on the Richter scale, almost like clockwork every 100 years or so. And the last one was in 1906, so they're actually quite overdue in San Francisco for another major earthquake, unfortunately. The last one ruptured gas lines underground and set the city ablaze and burnt the city flat down to the ground, or at least much of it. So this is the Carrizo Plains, where two plates actually meet up on dry land, and it's the locale for the source of many earthquakes. Here's Mount Hood in Oregon. Mount Hood produces tremors, typically 1, 2, about 3 earthquakes every year. It's a volcano in Mount Hood. As we scroll further down, what else is on this website? So we have a lot of derivations on oscillations. oscillations, whenever there's a restoring force on a particle or an object, so it vibrates about some resting position, so it oscillates back and forth. So we determine the physics of these oscillations. Most commonly a spring, a mass attached to a spring like a slinky. If you perturb the spring, it'll go back and forth like this. It'll oscillate back and forth. And there's quite a bit of physics involved in these oscillations. So we've derived the equations for oscillations to determine what's going to happen over time with these oscillations. And we've done several examples of these oscillations in this chapter. We also turn our attention to sound, the propagation of sound, how sound is measured in decibels, for example. Decibels has to actually do with the compression of the atmosphere. As the sound propagates, it causes air molecules to compress and refract back and forth. And it actually moves the atmosphere as it goes by a very small amount, maybe less than a billionth of a meter or so as the sound propagates. But this is a measure of decibel levels. Interesting to note that sound, the velocity of sound is dependent on the atmosphere. The hotter the atmosphere, the faster the velocity of sound. And the lower the temperature, the lower the velocity of sound. So we look at different examples of different kinds of sound levels. For example, a nuclear bomb has a decibel level of about 210. Simple conversation has a decibel level of just about 60 or so. And so there's everything that's sort of in between, above and below those decibel levels. But the reader will have a good gauge as to what the decibel scale is and how sound is measured. Now, we also talk about a very interesting concept called a Doppler effect. The Doppler effect deals with the stretching or the compression of sound waves, which also affects the frequency, right? As an object is moving away from us, the wavelength is being stretched. It gets longer and longer and longer because the source is moving further away from us. So the frequency drops. Frequency and wavelength are inversely related. As one increases, the other decreases. If the object is moving closer to us, the wavelengths, they shrink, but the frequency gets higher. And this is known as the Doppler effect. So if the reader has ever heard an ambulance, for example, coming towards you, that pitch, which was the changing frequency to higher levels, increases, but the wavelength decreases. As the ambulance leaves the observer and it goes further away, the pitch begins to drop, the frequency decreases, but the wavelength increases. So everything from determining where thunderstorms are located, which direction they're moving, Doppler radar is called, to tell you if to take cover from bad weather or if the bad weather is moving away from you, is based on the Doppler effect, bouncing microwaves off of thunderstorms and measuring the time delay for it to return. Measuring the depth of the ocean floor. And the ocean floor, oceans cover about 70% of the ocean floor, and less than 1% of the ocean floor has actually been explored with any great efficiency. We actually know more about the surface of the moon than we know about the ocean floor right here on our own planet. And how do we measure the great depths of the ocean floor with high degree of precision and accuracy and resolution? Is by sending sound waves from a ship on the ocean surface down to the ocean floor. It reflects off of the ocean floor, then the ship moves along and it does it again, and a computer plots the time delay as a function of latitude and longitude. Now if the sound wave that's being sent down hits a high mountain in the ocean floor, then it bounces back up in a relatively short space of time. But if that sound wave hits a huge trench in the ocean floor, it takes a much longer time. So that time delay it dictates what the ocean floor and the plot of the topography of the ocean floor is going to look like on a computer, a three-dimensional plot. So even mapping the ocean floor, Doppler effect is used for this. And in the grandest of schemes, even the expansion of the universe. How do we know the universe is expanding? Well, Edwin Hubble, the American scientist in the 1920s, measured the light from many stars and noticed that they all had one thing in common, that the light from all of these stars were what's called redshifted. That is, the wavelength was increasing over time, which means that these stars were all moving away from us, not just us, but moving away from each other as well. And what came out of that was the idea that, well, several things. One is that the Earth, and we are the center of nothing. And the stars that we see, they don't just all belong to the Milky Way, because up to that point it was thought that all stars that we saw in the heavens belong to the Milky Way. We know that is not true. There are many, many other galaxies, billions of galaxies for that matter. And again, they all have one thing in common, is that when you look at stars from our galaxy or any galaxy, they all show this red shift, this Doppler shift. So they're all moving away from us and from themselves. Ergo, the universe is expanding. So a great revelation made by this Doppler effect. The very same effect, like I said, that measures thunderstorms. When you get a speeding ticket from a radar gun, that's what it's doing. The radar gun sends out a signal, bounces off the metal parts of your car. There's a little chip in the radar gun that measures the time delay, and it's able to do the mathematics. There's a Doppler equation, actually. I can show you what it looks like. This is the idea of the Doppler effect, of the changing wavelengths and frequencies. This is the Doppler equation. And so radar gun does a quick mathematical calculation, and it tells the speed of the source being your car. So the police officer knows if to give you a speeding ticket or not. So the same technology that's used for giving a speeding ticket is used to measure the expansion of the universe. And so there are several examples to such an end. This is actually a picture of a black bear, the one that chased me down in the Rocky Mountains of British Columbia in Canada. He's actually eating my Snickers bar that I threw at him to distract him while I made it back to the car. The picture is a bit blurry because my hands were shaking. Being chased by a bear and all will do that to you. So there are several examples on the Doppler effect. And how to calculate the velocity of sound, the velocity of the source, and its applications to everyday life. This is one of my trips to Europe. This is in Austria, a town called Mittenwald, a fabled town of Mittenwald. And these are some ice caves high in the Alps, and inside of the caves, me standing at the entrance of the cave here, there are these structures. This is unique to our world, our planet, these ice caves. And the sound reverberations when you talk to yourself, these are frozen waterfalls inside of these caves that they never melt. And they play a lot of trickery on a person in here, because your voice, it comes back from all different directions with different kinds of time delays. You would swear you were in there with a whole lot of people. It's actually quite interesting and a bit spooky at that as well. So at the end of this chapter, the reader should have a really good understanding of mechanical waves, how they're produced, how they're transmitted, their properties, amplitude, wavelength, etc., etc. How sound waves are propagated, the calculation of velocities, the Doppler effect, and the many uses of the Doppler effect. So I hope you found this very interesting. As usual, thank you for your time.